usually when we're doing a volume integral, we'll be responsible for setting up the whole thing, so we'll need to find inequalities that describe the region of integration. So I've got some basic steps. We're going to start off by sketching the domain of the region. We're hoping that when we sketch the domain, that it looks like the region trapped between two surfaces, sort of maybe an upper surface and a lower surface, or a left surface and a right surface, or a back surface and a front surface. So we're hoping that there's going to be two surfaces. So, and then we're going to look for some region R, and our hope is that every point in the region R, if you put a vertical line through it, it will bust through the one surface, it will bust through both surfaces like this. So then we could just set up inequalities that describe the region R, and then our final set of inequalities will be from the one surface to the other surface, in this case from the bottom surface to the top surface, or in other pictures maybe we can break it apart, and our region looks like maybe the region between two surfaces that are left and right, or front and back. Set up our region R, and hopefully there's just in front and behind of every point there's just one place where it breaks through the surface. So let's look at an example so you get an idea of how this is done. So we're supposed to set up the integral to find the volume of the wedge cut from the cylinder x squared plus y squared equals 1 by the planes z equals negative y and z equals negative 1. Okay, so let's start sketching this. That was our first step. So cylinder x squared plus y squared equals 1. That'd be a circle of radius 1, but there's a z value here, so that means we get a cylinder that extends infinitely up and down. But we're going to cut that cylinder with the plane z equals negative 1, so we're going to cut it 1 below the xy plane. We're going to make another cut that's where z is equal to negative y. So when y is 1, z is negative 1, and then as we come back, we're going to go up through the origin and be higher up here. So we really have a shape. There's a circular cross section of the cylinder here, and then it's kind of coming forward, so we're going to see a shape that looks something like this. Sort of like the end of a lipstick, right? If you took a cylinder and you sliced it flat and then you sliced it at an angle, you get a shape that looks maybe a little bit like the tip of a lipstick. Okay, so we can see that we have this region R, and it is trapped between two surfaces, the surface where z equals negative 1 and the surface where z equals negative y. So all we'd have to do is write up bounds for this region. Well, looking down on the region, this is just kind of a problem from when we did planar 2D integrals. If you freeze z at negative 1, it was a cylinder of radius 1, so you just see a circle of radius 1. And I could set that up this way. I could say y is going to go between negative 1 and 1, and then the x value is going to go from the bottom of the circle to the top of the circle. Now, solving x squared plus y squared equals 1 for y gives me y squared, oh sorry, these bounds should be on x because it's vertical lines, gives me y squared equals 1 minus x squared, or y equals the plus or minus square root of 1 minus x squared. So we'd have bounds on y. Y goes from negative square root of 1 minus x squared to positive square root of 1 minus x squared. So that sets up the bounds for region R, and then for every point in region R, if you drew a vertical line or perpendicular line through that point, perpendicular to the region R, we would see that the z value starts at 0 and climbs up until it breaks through this surface where z is equal to negative y. So the integral that we would need to set up, these bounds don't depend on any variable, so they can be on the outside. And then these bounds depend on x, so they have to be inside the integral with respect to x. And then the z bounds depend on y, so they have to be inside the integral with respect to y. If we just want to find the volume, we would just take 1 times, let's see, the innermost bounds were bounds on z, and then those next bounds were bounds on y, and the outermost bounds were bounds on x. So we could do the integral in this way. That would get us the volume, because basically we're taking 1 times a little bit of volume, right? A box that was dx by dy by dz would be a little bit of volume. If we want the mass, since we're in 3 dimensions, the density would be mass per volume. So we would just do the integral from -1 to 1, and from negative square root of 1 minus x squared to positive square root of 1 minus x squared, and then from 0 to negative y. But instead of integrating 1 dv, we're going to take density dv. So that's going to be x squared y squared plus z to the 4th. That's the density dv. So if that's mass per volume, and dv is a tiny volume, then that product's going to be a tiny mass. And basically what we're doing is we're summing up all the tiny little bits of mass. Here's a little more practice in setting up volume integrals from a description of a situation. We're supposed to find the volume of the region in the first octant, so that's where x, y, and z are all positive. Bounded by the coordinate planes. That would be, the coordinate planes would be the xy plane, the xz plane, and the yz plane. And this surface, z equals 4 minus x squared minus y. Okay, so this surface, if it was 4 minus x squared minus y squared, it would be an elliptic paraboloid opening down. But it's only parabolic, it's only quadratic in the x term. So if we froze y equal to 0, then it would open down like this. But if we freeze x equal to 0, then this surface just kind of goes down linearly like this. So what we really have until it crosses through the, it's going to cross through in a parabola down here, right? So we've got a shape that looks something like this. Okay, so there's a couple ways to look at this surface. One way would be to describe this region R in the xy plane, and then the z value, for every point in R, the z value starts at 0 and goes until it breaks through this parabolic cylinder for z equals 4 minus x squared minus y. So we just have to figure out what is this region R. So to figure out what that region R is, I'm going to set z equal, this region R is where z is equal to 0. So if z is equal to 0, then we have this boundary right here. It's going to be where 4 minus x squared minus y equals 0, or where y equals 4 minus x squared. So if I just look at the region R, I'm just going to draw it in the xy plane so that I can see it. 4 minus x squared, y equals 4 minus x squared is a parabola. When x is 0, it's 4, and when x is 2, it's 0. So we have a parabola like this. And we can set up bounds for this pretty quickly. We could just say x runs from 0 to 2, and then y, for every x value between 0 and 2, the y value starts at 0, and it climbs until it hits the parabola, and the equation of the parabola is 4 minus x squared. So now we've got bounds on our region R, and then for every point in R, the z value starts at 0 and goes up until it hits the parabolic cylinder, 4 minus x squared minus y. So to set up our volume integral, we could just do the integral from 0 to 2, and then inside of that is the integral from 0 to 4 minus x squared. That's the y integral. And then the z integral is 0 to 4 minus x squared minus y. Notice that the bounds, this integral, we just do 1 dz dy dx. Notice because the inequalities for y depend on x, the integral with respect to y has to go inside the integral with respect to x. And since the inequalities that describe z depend on x and y, that integral's got to be inside both of those. So we have to do this integral in this particular order when we set up the bounds this particular way. Of course, there are, in general, there's 2 choices for the inside variable and 2 choices for the variable outside of that, and then there's 3 choices for the inside variable and 2 choices for the variable inside of that, and then only 1 variable remaining. So there's usually 6 ways, 1 times 2 times 3, for the multiplying the choices that we can set up an integral like this. Now to get the mass, we'll we'll take density. Since density in 3D is mass per volume, we'll just take the density times the volume to get a mass. So same region, so same bounds. All it changes is the integrand. So the density function is x plus y plus z. So we'll have to take that function and multiply that by dz, dy, and dx.